Welcome. Today, I'm going to take you on a journey that we took to build our AI serving platform using operators, the challenges we faced, and how we overcome those with a design pattern. So, yeah, I love Kubernetes, and I guess you also do. So if you also love Kubernetes, I guess we all love operators. And let's see what, and if you don't, perhaps you will love it after this session. So what's operator? In a nutshell, operator extends a Kubernetes core API. And let's say in more descriptive way, and by Kubernetes documentation, operators are software extension to Kubernetes that make use of custom resource to make applications and their components. Operators follow Kubernetes principle, notably the control loop. So essentially, control loop are the execution logic, and resources are the data. And operators here are the autopilot of your cluster. That's cool, right? So how controllers and resources are doing that? So controllers are checking Kubernetes cluster and your desired state from your resource and reconcile these two. So that's simply put. So now that we know what's operator, what is controller, what is resource, how should we start to build our operators? So how it started. So you go search for a framework, and you will perhaps go to the Google saying, OK, best framework for developing Kubernetes operators, and you will probably hit operator SDK. At least that's what I did. And you will go to start with a tutorial how to build your first operators. And what's better than the original website? How can I build one? You will start following the quick starts, how to build your operators, and you will perhaps build your first memcached operator by following the tutorials. And you're happy, so based on this hype, you will start building your operator on top of the tutorial, what you learned. And congratulations, now you have your first operator, and you're so happy with that. But this was me 2 years ago. How it's going after that? The controller logic gets complex very quickly. It's not, it will be so many things that you never anticipated the first day. And the CRDs are like the stone, and when you want to change something that is like carving in a stone, and it's out there, it's a central API, you cannot change it easily. And above all, for the platform engineers, it's the headache that only the creators may touch the operator code after 2 years, and everybody will come to you saying, OK, I want this, I want the other thing, and you are responsible for all of that. And nobody else can do that. So this was when we were at this point of the time that we developed some of the controllers and operators. And we see this irony that cloud-native developers build monolithic operators. I said, this is something that we should not do. So what should we do with this monolithic operator, with this big monolith? So we all know the answer. Usually it's divide and conquer. So on the divide part, we can have modular CRDs. So we can split our CRD into smaller pieces of specs. So that's the divide part. And for the conquering part, we can have microcontrollers, which each of these microcontrollers take care of this specific CRDs, which we identify that they are for a specific task. So what a controller does, so let's recap. So controller reconciles the cluster. And in doing that, it means that it needs to translate your custom resource to built-in resources, or let's say other resources, which in turn and finally will be a built-in resource that Kubernetes knows and operates with that. So we want to decouple CRD translation from controller so that the logic is not how to build these ones. And we already know a tool that its work is to translate values into manifest by using a template. And I guess you can all agree with me, and you may already click what it is, and it's Helm. It's the main job of Helm to get some values and with the templates to create manifest. So when there is such tool there, let's use that in our benefit and put it in our design. So with values and templates. And now we have our resource, which we want to make a connection. For the connection, what we came up with was to come up with something called trait system. So the developer or the application developer will care about how to define the characteristics of the resource. For example, the type is stateless or the size is medium. So they don't care if you want to deploy it whatever way and translate it to whatever way in Kubernetes. They will saying that, okay, this is a stateless. That's how a developer care about this resource. And we are linking the values and templates to the resource by these annotations. So I'm going to get in more technical terms right now. But before that, we need to first see the structure of the code base. So we will have charts. I guess they don't need introduction, values, and templates, plus helpers. So for the values, if we want to go into that, like for example, for the type, we define a Helm value, and it's type, and it can have a default value because sometimes people may not set the characteristics. So we say, okay, if it's not set, it's stateless. And we have some sort of conditions. If it's stateless, we know that we need to use a deployment template. If it's stateful, we do have a stateful set template. The same goes also for the size. For the size, having one default, let's say default replica 1. If it's small, a replica is 1, medium 2, and large 3. The point here is that it enables us to have an abstraction level between the size and the actual implementation, which is, for example, the number of replicas. How many replica do you want? And this can be different per cluster. Like, for example, for T-shirts, medium means something in Europe, and if you go to China, medium means something else. If you go to US, medium means something else. But all are medium. So you have this abstraction of calling this workload or this service as a medium size, but the platform engineers are responsible for defining what medium means in my cluster. So now let's see when we are doing it this way, how big will be the main file. The main file will be as simple as this, like include trait.type. And we define trait.type in our helper. And in the next two lines, we get the value from the resource. In this case, it's stateless. And we also need to know what's the default value if it's not set. It's also a stateless. And then we are going to iterate over the conditions to see for this value, what's the template. For stateless, we know from the values that the template is deployment. And we're going to continue. So this is the most important part, is that, so now we know that the template is deployment. Now we need to include that. And means that we need to include trait, the template, the deployment, which we do have it here as an deployment.yaml, which is just like a Helm template. We all know that, how it's like. So we need to define that, and then this way, we manage to connect Helm to our templates with values in the resources. So now we do have configurable modules, configurable controllers, which can be configured through values and templates, and all can be done not inside the code of controller, not inside, let's say, you don't need to write a Go code, or you don't need to write Java. It's all Helm, and Helm is somehow a well-known. So like DevOps people know how to write this Helm templates. Platform engineers knows. So it's a common language for configuring your operators, or let's say controllers. So is it worth the effort to have all these abstraction layers, these connections? So if you're not still convinced that it works, and you may say, for example, that, okay, my operator is not that complex, I don't need this level of abstraction. Then if it's not a complex thing, I would suggest considering Helm in total, because operators are mostly for complex structures, for complex application logics. And if you are still not convinced, I'm going to remind you of this library, unstructured. So if you know it, you know how of a big of a headache is working with an unstructured API. And especially for external CRDs, when you have external CRD, and even especially if it's not, it doesn't have the API in your language. For example, you're writing in Go, and the API or the other controller, which they define the CRDs, are in Java. So you don't have a way to directly import that, and you have to use unstruct, and that's a headache, believe me. And you probably, some of you may already know that. So I would say definitely, of course, it's worth the effort. So let's recap. So for the controller, the task was to reconcile cluster, which is the actual state, with the desired state of your Kubernetes resource. And we managed to delegate this translation of Kubernetes custom resource into built-in resources. So we are now getting rid of this. So now let's see how these controllers work with this microcontroller design pattern. So we will have a number of microcontrollers to take care of specific parts of specs. But for that, first we need a coordinator, which controller calls that coordinator, and the coordinator knows from the spec how to divide these things, to send it to different microcontrollers. And what do we want from the controller here? From a controller, we want values, because we have our templates in our Helm. So if we have the values from the controllers, which they need to understand the logic and then say us, okay, this is the value that you should set, then we already have our manifest creation process. So we need to get the values from them. And so you can have also we can take a look at how we structure the code base. So we will have a microcontroller.go, which is the main or big control loop. We do have a coordinator, which knows based on this big spec how to divide it and to send it to microcontrollers. And we will have a number of microcontrollers. So we are still adhering to the best practice of Kubernetes to put all of these threads, things in one container for the performance sake. But still, we do have this flexibility to add more microcontrollers, to add more logic, or modify that. For example, if you want to change your HTTP controller or microcontroller, you know where to find it, how to edit it, and how it will work. So to putting everything together, I guess we established that the custom resource will be linked to the Helm templates by the traits. And we also do have a controller which reads from this CRD or custom resource, let's say, is your desired state. And using Helm and the connection with the resources to the Helm, it will create the manifest. Now it's time to get the actual state from the cluster. And then comparing these two, applying the difference to your cluster. So the benefit of this is that it will also give us the separation of responsibilities. The developers are interacting with custom resources. They define the resources through characteristics. Of course, they need to still fill the spec. And the DevOps or SRE security people know how to configure this translation using Helm for different types of clusters. And the job for the platform engineer will be to develop these microcontrollers and also creating this, maintaining the main controller loop coordinations. This work is part of our bigger project. This is the core of one of our projects, which is called ESIDA, for Evolutionary Changes in Data Analysis. So we are trying to help data scientists so that they can serve their models easily, and our system is built on top of these operators. So what we're missing here is the actual scientist. So the actual scientist in our platform can use a user interface to create these beautiful pipelines, or they can use our software SDK so that it can automatically generate custom resources using CI/CD pipelines. So to let you know what kind of operators we do have, we first need to see what's the application, what's our application. So as I said, it's a AI serving platform that you can create your pipelines. For example, we do have a data source. It's a module which sends data to an LLM. Then we do have a validator taking the stream of data and then perhaps validate or reject and give it some score. And with this technique that we do call is, let's say, generalization on top of things, so we see all of this as link. We can also have loopbacks. So we can also send the data to a planner that, based on the evaluation, can say, okay, what should be the next prompt? How we can tune the prompt so that it works better for the next data based on these evaluations. So the whole thing, we call it a pipeline, and we need a pipeline controller for that. The boxes are module controllers, modules, and we do have a module controller for that. And it doesn't matter how do you want to deploy that, because we have a versatile controller that can pick any kind of modules and translate it in any form so that it runs. And for the links, we do have a link controller, also the same design pattern. And on top of that, you can also configure the modules, for example, change the threshold here, and see the different results on the fly. So at the end, you don't need so many controllers. You need configurable controllers. You need controllers you can configure the way you want for different types of resources, for different environments. So this is how we built our operators. They are easy to develop, configurable, maintainable, and we do have a clear responsibility for each person in this organization, so there will be no dispute. So I hope by now you also love operators. My name is Mostafa Hadadian. I'm CEO and founder of CRDL. CRDL stands for Continuous AI Delivery. And I'm also finishing my PhD at University of Groningen. I used to be a data engineer, data scientist, leading this team of data engineers, team of data scientists together, leading the projects, and been also a platform engineer. So I saw the whole spectrum and tried to build something that all of the stakeholders has a saying in this platform, so they each can know how they can contribute to this application. So if you like, you can scan the QR code, and let's stay connected. Thank you.